Today we are at the Department of Physics, Sri Shivaji Education Society's Science College, Nagpur. We are assembled here to have hands-on experience on four vectors and its use for Compton Effect and a few more things. So, I would like to revise vectors first of all. The basic vector we write A bar as having components A1, A2, A3. So we express this as A bar equal to A1 I cap plus A2 J cap plus A3 K cap. If you find the dot product of A bar with respect to with A bar, it is A1 square plus A2 square plus A3 square. So here I am going to define a new 4 vector. And I am going to use a capital letter, capital A, to represent a 4 vector, and this 4 vector has components A0, A1, A2, A3. This can also be written as A0, A bar. So A bar is your normal 3-dimensional vector. Now here we define the inner product of capital A with respect to capital A. So this is defined as A0 into A0 minus A1 into A1 minus A2 into A2 minus A3 into A3. So this is the definition of product of 4 vectors. We can call this as inner product of A with A. If we have another vector B having elements B0, B1, B2, B3, then we can have product of A and B as A0, B0 minus A bar dot B bar. This is a compact notation. Here A bar, small a bar and B bar, these are normal vectors, 3-dimensional vectors. Now we can explore this for relativity, because in relativity we represent event. Event we represent by Cp, first coordinate having dimensions of length, then x, y and z. So in generalized notations I can use x0, x1, x2, x3. Now you can find x square. X inner product with x. This is a quantity that we can call x square, and this will be c square t square minus x square minus y square minus z square. So in the notation of 0, 1, 2, 3 suffixes, it can be written as x0 square minus x1 square minus x2 square minus x3 square. So this can also be written as x square equal to c square t square minus r square. where R has usual magnitude of three-dimensional vector. Now this quantity in special relativity has a special status that we call interval, and interval is an invariant quantity in relativity. That S square we write as C square T square minus, and again writing X square minus Y square minus Z square, and it is same for all inertial observers. So C square T dash square minus X dash square minus Y dash square minus Z dash square. Now those who are conversant with special relativity and to some extent they know what is invariant quantity in special relativity. It is called as interval, and that interval is defined by C square T square minus X square minus Y square minus Z square. Now here we have transformation equations as x0 dash equal to gamma times x0 minus beta x1, where we are having a reference coordinate system which is moving along x-axis, and that moving coordinate system will be represented by s dash, and s dash is moving with velocity v with respect to s. Then this is Lorentz transformation equation. Another one is x1 dash equal to gamma times x1 minus beta x0. So this similar format we can explore for velocity transformation, momentum transformation, acceleration transformation, and so on. Now here the meaning of beta is v upon c, where v is the inertial, v is the velocity of inertial frame of reference, and gamma we define as 1 upon under root of 1 minus v square by c square. So this is the abstract of relativity that I have given to you in these last equations. Now here we have s square, which is pertaining to capital X square. So inner product of event when we perform with itself, it gives a quantity which is Lorentz invariant, and the beauty of this definition is that we are having Lorentz invariant quantities. Now I want to make a simple argument, and by virtue of that, we will be skipping derivation of Lorentz transformation, directly will be landing upon the transformation equation. Now, the argument is that if we stick our event to origin of inertial frame S dash, which is moving with velocity v with respect to frame S, then the moment we stick our event to the origin of S dash coordinate system, it means that x dash is equal to 0, y dash is equal to 0, and z dash is equal to 0. So this last equation becomes s square is equal to c square t square minus x square minus y square minus z square. This is equal to c square t dash square. Because we have chart event to occur at origin of S dash. So that is the simple argument that we have made here. Now, in this situation, if S is greater than 0, then that event we call as time-like event in special relativity. So if S is greater than 0, it is time-like. If S is equal to 0, this is light-like. And if S is less than 0, it is space-like. These are the technical terms that are being used in special relativity. Now, I want to explore this equation. This S square equal to, I am taking C square, T square common, and inside bracket it is 1 minus before that, I would like to make a differentiation for infinitesimal change, and for infinitesimal change we can have C square dt square minus dx square minus dy square minus dz square equal to C square dt dash square. So this is infinitesimal variation of interval of event. Now we can take C square dt square common, C square dt square inside bracket 1 minus dx square plus dy square plus dz square divided by C square dt square. This is equal to C square dt dash square. Now, this quantity dx square plus dy square plus dz square can be treated as dr square, and we'll be having C square dt square inside bracket 1 minus dr square by dt square multiplied by 1 by C square. This is equal to C square dt dash square. So this quantity is velocity. C square on both sides, and we can take under root, and we can write dt dash is equal to dt into under root of 1 minus v square by c square. So dt can be written as dt dash upon under root of 1 minus v square by c square. More useful form that I am going to explore is dt upon dt dash. Instead of dt, some people prefer to use tau. This is equal to gamma. So this is one important relation that we have found out, and there is no need of Lorentz transformation equations. However, they are having this kind of format. Now, if we want to find velocity, we differentiate the event. So, event we are writing in terms of capital X. Now, the first thing we have discussed is 4 position, and that 4 position we have written as X. This is CT R bar, CT R bar. This makes representation of 4 quantities like CT, X, Y and Z. So I am using a compact form to write that. Then by differentiating this position, we can obtain velocity. So for velocity is the second quantity that we are having for velocity, and I am going to use capital U later to represent for velocity, and I would like to differentiate this for position with respect to tau, that is proper time. Why with respect to proper time? Because proper time is a good candidate. Proper time is a quantity which all inertial observers can agree upon. It's not normal time. Everybody will have different times in their different frame of references. But the definition of proper time is universal for all. So I want to differentiate position with respect to proper time. So dt tau of capital X will represent for velocity. Now I can use a chain rule, Vx by dt into dt by d tau. So dt by d tau is gamma. So u, that is for velocity, is equal to gamma times d dt of this event x. So this event x is ct comma r bar. Now vector I am writing as components in the parenthesis. Now this is equal to gamma times c is an absolute constant, so it is not affected by differentiation sign, and dt by dt will be 1. So for velocity can be written as gamma times c into r dot, that is normal time derivative of r. So that makes a normal velocity. So gamma times c comma v bar. 3 components and one more component added to that, that is c. So this is for velocity. Now we shall form inner product of u with the way we have found inner product of x with x. We have obtained a quantity which is Lorentz invariant, and that we call interval in special relativity. So when we are talking in terms of space and time together, that leads to Minkowski space. So basically, this discussion is for the one who has already studied special relativity. Now, here I want to perform inner product of u with respect to u, and obviously, if I am writing these two quantities here, so gamma into gamma will be gamma square, and it will be c square minus v bar dot v bar will be v square. So product of two 4 vectors, inner product of two 4 vectors leads to a scalar quantity. And this scalar quantity is invariant as we have seen in case of x. Let us see in case of u what happens. So gamma square into c square inside bracket 1 minus v square by c square. So if you look at gamma, when we have gamma, it is 1 upon under root of 1 minus v square by c square. So if you work out gamma square, this will be simply c square. So this and this will be cancelled. So you already know that velocity of light is an absolute constant, which is axiom, second axiom of Einstein's special theory of relativity. So inner product of u with itself, it's a quantity which is Lorentz invariant, which is universal. Now we can go ahead for third definition, that is for momentum. And as you all are aware, momentum is a very interesting quantity, and this quantity in fact offers us a wonderful equation that Einstein's theory has given to us. So I am going to define momentum using letter capital P. And capital P, by definition, is mass of the object into velocity is capital U. We have already defined that. So capital P will be equal to m0 times gamma inside bracket C comma V bar. So these are the components of fourth momentum. So first component is I am calling P0, and second component I am calling P bar. P0 is the new element that we are encountering here, whereas P bar is our usual relativistic momentum. So P0 is m0 C times gamma, and P bar is your usual momentum m0 gamma into V bar. So m0 times gamma, this makes relativistic mass. Relativistic mass into velocity, this leads to relativistic momentum. So this is nothing but the relativistic momentum. Now here, this is a very interesting quantity which I would like to expand. m0 times C into 1 upon under root of 1 minus V square by C square, that can be written as 1 minus V square by C square to the power minus 1 by. Now we can make a binomial expansion for this, and ignoring higher order terms, we can write this as m0 C into 1 plus V square upon twice C square. So if you expand the bracket, P0 will be m0 C plus 1 by 2 m0 V square into 1 by C. Is it okay? Yes. So what does this represent? This represents a quantity which is quite similar to what we imagine. Now let us multiply both sides by C. C into P0 is equal to m0 C square plus 1 by 2 m0 V square. So it represents rest component of energy. m0 C square is the rest energy of the particle, relativistic energy of the particle, and 1 by 2 mv square, it represents kinetic energy. So C times P0 is the total energy of the system, rest plus kinetic. So here, this equation offers me that P0 is equal to E upon C. P bar is our normal momentum, whereas P0 is energy upon C. Okay. Now, we shall explore these equations further. For momentum P is equal to, I want to write that it is P0, comma P bar. Is it having a equation? That is equal to E upon C, comma P bar. So this P bar is normal relativistic momentum. The another definition of P that I have written there is in terms of M0 gamma. This is M0 gamma inside bracket C comma V bar. So we have a couple of definitions of the four momentum. Now let us work out inner product of P with itself.
Okay, so this will be P0 square minus P bar dot P bar will be P square. So this is equal to, let us plug in these values, M0 square gamma square into C square minus V square. A bar 4 vector A into 4 vector A, we have written A0 square minus A bar dot A bar. In the same fashion we have done this. So if you take C square common, M0 square C square gamma square into 1 minus V square by C square. So this cancels out. So we are left with M0 square C square. So this is P dot P. Again, it is very obvious that the quantity is Lorentz invariant because M0 is proper mass. The definition of proper mass is that the observer is in the state of rest and the object which is being measured, that is also in the state of rest. And when this business of measuring mass is done, all inertial observers will agree upon that. So that is a universal constant. Now I have this definition also to write in terms of inner product of P with respect to itself. So it will be E square by C square minus P bar dot P bar will be P square, where this P is relativistic momentum. Now we can compare these two results. So just immediately I will plug in the value M0 square C square equal to this. And if you look at this equation, it is that famous equation that theory of relativity has given us. So let me multiply both the sides by C square and carry this P square on right hand side. It will be E square equal to P square C square plus M0 square C to the power 4. So I think in 15-20 minutes we have derived the outcome of special relativity, that equation which we have used every now and then in Compton effect and various considerations where velocity involved is high. So this is how the four momentum inner product offers us the famous Einstein's equation. Now we can, in the similar way, we can define four acceleration. So how will we define four acceleration? We have to find the rate of change of momentum. The basic definition of acceleration is rate of change of momentum. So instead of differentiating it with respect to normal time, it would be customary to define with respect to proper time.
Again, we shall use that chain rule, dp by dt into dt by dt. The moment you talk about acceleration, you are leaving behind the definition of inertial frame of reference. Basically, inertial frame of reference is that frame wherein the velocity is constant, uniform throughout. But as we are making a change in that velocity, this factor gamma is now no longer constant. So here A is equal to gamma times ddt of 4 momentum, and 4 momentum is m0 gamma c comma v bar. So here m0 gamma inside bracket we have c into gamma dot. The meaning of gamma dot is d gamma by dt. When physicist is putting a dot on a letter, it means it is a time derivative. Now, comma, then we have gamma into v bar, and we have to find derivative of that. Again, you have to use chain rule, and that gives us gamma dot v bar plus gamma into v bar dot. So v bar dot means acceleration, your normal acceleration. So the formula for acceleration is m0 gamma inside bracket c gamma dot comma gamma dot v plus gamma a bar, where small a is representing usual 3-dimensional acceleration. Now, I believe that inner product of A with respect to itself for you students to do on your own. The next point I would like to discuss that can we apply this representation for photon. Can I write 4 vector for photon? Use capital K to write momentum, 4 vector for photon K, and this time I am talking about 4 momentum. So normally P we write m0 gamma c comma v. The basic definition is E by C, P bar. So 4 vector K for photon can be written as E, energy of the photon, h nu. So h nu by C is the zeroth component of the momentum, and then next is momentum. Momentum of the photon, you know that it is h nu by c. So we have both the elements, zeroth element and the momentum vector same. And if you perform k dot k, it will be 0. So it is very obvious that k dot k will be 0, and that offers again an invariant quantity. Now, if you are comfortable with this, we can apply these concepts in quantum mechanics. In quantum mechanics, BSc final year students and MSc students, they know that a free electron cannot absorb a photon. You must have done this derivation sometime. So we can prove that using 4 vectors also, and then we can go ahead for some advanced application. So the first application I would like to discuss applications of 4 vectors. The first application is free electron cannot absorb photon. Now, first we shall assume that a free electron can absorb photon, and will let something happen wrong, and then we claim that what we have presumed is a wrong way of thinking. So the first approach is that let a free electron absorbs photon. I would like to show that as, let us suppose that this is a photon, so the frequency variation I try to show, and this is a free electron at rest, and the product of this is a scattered free electron with some momentum. So let us suppose that K is the momentum for vector of photon, P is the momentum for vector of electron which is at rest, then P dash is the momentum for vector of the photon after absorbing photon. Momentum for vector of electron after absorbing photon. Now, K, normal conservation equation, all momentum before collision is equal to momentum after collision. So the conservation equation is K plus P is equal to P dash. This is the conservation equation. Now, K can be written as h nu by C, or you can write that as h cross K bar. H cross K also you can write is one and the same thing. There should not be anything wrong if we write h cross K. But let us go ahead with h nu by C, comma h nu by C. So this quantity is capital K. Then capital P, that is for momentum of electron in the state of rest. The for momentum we write m0 gamma C, comma rest है इसलिए V will be replaced by 0. Okay, so m0 gamma inside bracket C, comma 0. Then the electron which has absorbed the photon is moving with some
velocity and will have some momentum. So P dash can be written as m0 gamma inside bracket C, comma V bar. Now I want to play with this conservation equation. So unless I do some perturbation, nothing is going to happen. And that perturbation is finding inner product of the equation with itself. So inner product of the equation with itself, P dash dot P dash. So I am finding inner product of P dash with respect to itself, that is equal to K plus P in one bracket multiplied by K plus B, P in another bracket. So K square, you can call this as K dot K plus P dot P plus twice K P. Okay? So here we have to work out that mix inner product. Now, let us work out P dash dot P dash. It will be m0 square gamma square. So I am finding from here, okay, into C square minus V square, V bar dot V bar rather. So it will be C square minus V square. This is equal to K dot K is 0. We have already done it here. For photon, K dot K is 0. So this is equal to 0 plus P dot P, M0 square gamma square C square minus 0. Now in this situation, if the object is not having relative velocity, velocity is 0, so what will be gamma? It will be 1. Why? Because gamma is equal to 1 upon under root of 1 minus v square by c square. So velocity of rest electron is 0. So 0 upon c square will be 0, 1 minus 0 will be 1, and under root of 1 will be 1, 1 upon 1 will be 1. So here this gamma square is not having any sense, because it is 1 plus 2 times k dot p. So second component is being multiplied with 0, so that is vanishing. So h nu by c multiplied by m0 gamma. This gamma is 1. So m0 c 2 times h nu by c multiplied by m0c. Now here we can take c square common, m0 square gamma square c square 1 minus v square by c square. So this quantity is cancelled, we have seen in earlier cases also. That is equal to m0 square c square plus 2 times h nu m0. So here we are left with m0 square c square equal to m0 square c square plus twice h nu m0. So this quantity is also cancelled. It means that h nu into m0 is equal to 0. We have electron that is having rest mass m0. It is not a zero quantity. It has some numerical value. So we have considered a photon, and the product of two can be 0 only when one of them is 0. So both are, product is coming 0. It means that this is a contradiction. We have arrived at contradiction because we have a wrong assumption that a free electron absorbs photon. So this is not feasible. That is why we landed with a contradiction. So it means that, so 4 vector proves that a free electron cannot absorb a photon. Now I hope everyone is conversant with Compton's effect, and now we can apply this 4 vector theory to Compton effect, and in 5-6 steps we can derive that formula for what you call delta lambda, Compton shift. The incident photon has 4 momentum k. The free electron has 4 momentum capital P. Then in one direction the photon is scattered, and that photon can be charged using k dash. It is an angle phi, and the electron recoils in some direction. Let us suppose that it recoils in some direction like this, and it is expressed by p dash. This direction is suppose theta. And now our business is to write 4 vectors for all. So this is a genuine example that we are going to discuss. So k is 4 momentum of the photon. I shall write h nu common, h nu by c common rather, 1 comma 1 0 0. I am writing all 4 components because I have to account for directions. So it means that a photon of momentum h nu by c, zeroth component, and the momentum component is incident along x direction. So second one is pertaining to that x. This is zeroth component and this is x component. Y and z components are 0. It means that the third direction and fourth direction, they are 0. So the motion in this direction is 0 and perpendicular to plane of the board, that is 0. And then the second quantity is free electron at rest. So M0 gamma C 0 0 0. Okay. Then it is scattered in some direction. So it has 2 components. One you can write by cosine component and another by sine component. So K dash is equal to h nu by c. Zeroth component is h nu by c. Okay, and one component is h nu by c cos of theta, h nu by c sine of theta, and nothing is happening in the z direction. We are not leaving the plane of the board, so the z component is absent. Then P dash is M0 gamma times C. Then velocity components we have to account for, and those velocity components will be v cos phi comma v sin phi 0. So here you can resolve this. Here also you can resolve the components. I think I have interchanged that. मैं इसी को करता हूँ. So phi is the direction of the scattered photon. So phi should appear here and theta should appear here. Now the conservation equation will be momentum, 4 momentum before collision equal to 4 momentum after collision. So the basic conservation equation will be k dash plus p dash. So I can write p dash equal to k plus p minus k dash. So I shall find inner product of p dash with itself. So p dash dot p dash is equal to k dot k. I shall write k square, no harm in doing that, plus p square plus k dash square plus 2 times k into p minus k into k dash minus p into k dash. Is it okay? Am I right? Now here we have to understand this we shall work out these squares. K dot k 1 minus 1 will be 0 multiplied by anything. That won't make any difference. Then here p dot p will be m0 square gamma square c square minus 0. Okay, that will be c square. Then k dash dot k dash h square nu square by c square 1 minus cos square plus sin square. Cos square phi plus sin square phi, that will lead to 1. So 1 minus 1. So this will be 0. Then this component p dash dot p dash, this is equal to m0 square gamma square into c square minus v square. Sin square theta plus cos square theta will be 1. Now mixed product we have to work out k into p. K into p. So m0 gamma h nu by c. 1 into c will be c minus 0. So this will be simply multiplied by c. So this will be m0 gamma h nu. This will be one part. Then k dot k dot k dash. Let us try to work this out. K dot k dash. This one is k, this one is k dash. So h nu by c, here I should have given dash to this quantity.
Yes.
K dash should have frequency nu dash, different frequency. So this nu dash, this should have been nu dash. Now k dot k dash will be h square by c square nu dash. So this is that product. 1 into 1 will be 1 minus 1 into cos phi will be cos phi minus 0 into sin phi will be 0 and 0 into 0 will be 0. So those who are familiar with the equation can identify this quantity 1 minus cos of phi, which is appearing in the Compton shift. Then the next quantity that we need is p k dash. K dash is equal to m0 gamma into h nu dash by c. We are finding p k dash. So m0 gamma into h nu dash upon c multiplied by c minus 0. Okay? So this is m0 gamma h nu dash. Now we can plug in all the values, and the equation is p dash, this conservation equation I am using, p dash dot p dash is m0 square gamma square. So this quantity is m0 square c square. Okay, this needs one more simplification step, that m0 square gamma square into c square into 1 minus v square by c square. So the quantity in the bracket and this gamma square is cancelled. So m0 square c square is equal to second quantity k square. K square is 0 plus p square. This is m0 square c square, because when it is in the state of rest, gamma has to be 1 because velocity is 0. So m0 square c square plus k dash square, this is 0, plus 2 times we have kp, that is m0 gamma h nu. So is this gamma unity? In case of p, gamma is 1. Am I right? So it is m0 h nu. Then the another quantity is kk dash. It is h square by c square nu dash into 1 minus cos of phi. This is with minus sign. Second quantity kk dash is with minus sign, and then pk dash. Pk dash is this quantity minus m0. Again p is involved, so for p gamma is unity. So this gamma should be replaced by unity. So m0 h nu dash is the only quantity left. So bracket complete. So you can cancel out these two terms, and then we are left with m0 h nu minus nu dash m0 h nu minus nu dash, that is equal to h square upon c square nu dash into 1 minus cos of theta. So you can take this m0 here, one h can be cancelled, and you can carry this nu dash on left hand side. So nu minus nu dash divided by nu dash, this is equal to h upon m0 c square into 1 minus cos of phi. So nu upon nu dash will be 1 by nu dash, 1 by nu dash minus 1 by nu. I shall multiply this by c on both sides. So this will be equal to h upon m0c into 1 minus cos of phi. So this is lambda dash minus lambda equal to lambda c Compton component into 1 minus cos of phi. So quite easily we can encounter with the final equation that we learn as the derivation of lambda or derivation of shift in the wavelength.